This is PHYS30141 video 25. In the previous videos, we looked at how the incident, transmitted and reflected components of an electromagnetic wave would be related to each other when the electromagnetic wave was incident normally on a boundary between two media which had different optical or electromagnetic properties. And in those derivations, we assumed that the electromagnetic wave was incident normally to the boundary between those two media. Now we should look at the similar case when instead of being at normal incidence, the incident electromagnetic wave can be at some angle, theta I, to the boundary. So again, we consider dielectric media where there is no conductivity. And on either side of that boundary between the two media, we have a relationship between the frequency and the corresponding wave number, which is given by the refractive index, or equivalently by the relative permittivity. And we haven't yet said that theta I and theta R are equal to each other, but we're going to obtain that during this derivation. And we assume that the electromagnetic wave has some wave vector direction, so this value k subscript I indicates both the direction of the electromagnetic wave and its magnitude. And our job is to calculate what kr and kt are correspondingly for the reflected component and for the transmitted component into medium 2. And because we're going to be using I for the incident component, we're going to write for this section that the square root of -1 is equal to j. So it's a brief note and temporary notation change. So I now denotes the incident electromagnetic wave. So the incident electromagnetic wave at any given position and time obviously oscillates at some frequency omega, and this ki dot r, where r is some location, ki dot r lets us know what the spatial phase is at a given time. So for each of the wave components, the incident, the reflected and the transmitted, they have a magnitude and of course a corresponding direction given by this constant value, and they also have corresponding phases at any location given by the dot product of the wave vector direction with the location at which we're observing. And of course, if we know the electromagnetic waves, we know their electric components, we can work out their magnetic components by taking the cross product of the electric field with the wave vector. Now, another thing that we know is that there is continuity of the parallel components of the magnetic field and the electric field at this interface between medium 1 and medium 2. So we're going to label our coordinates. Z is the distance away from the boundary between the two media, and x is the distance along the surface between them. So we're going to take z equals 0 as being the point at which the surface boundary between medium 1 and medium 2 occurs. So the continuity of the B parallel and E parallel parts of the electric field at this boundary demands that all the phases are equal. So at the boundary, ki dot r, kr dot r, and kd dot r are all equal to each other, because if they were not, then the electric fields would be out of phase with each other at the boundary. They would not add up correctly. So I can say that ki dot r, kr dot r, and kt dot r at the boundary are equal to each other. However, we also know that we can write out explicitly that ki dot r is explicitly kix, the component of k in the x direction, times x, plus kiy, the component of k in the y direction, times y, plus kiz. And of course this is true for the reflected and transmitted components as well. So of course, when I simply take z equals 0, I can write out that the dot product ki dot r is equal to kix times x plus kiy times y. So we should think of this as being how the phase of the electromagnetic wave varies as a function of distance along x, and equivalently as a function of distance along y, which of course here is out of the page. So let's look at that plane in which Ki and Kr and Kt live. So we're thinking about the plane formed by the direction Ki, where this plane must be perpendicular to this boundary here. This is the boundary between medium 1 above and medium 2 below. Because Ki dot r is equal to this, then I can write down that Kry and Kty must be equal to 0. The waves must lie in the same plane. So Kr and Kt must lie in the same plane that I formed by taking this Ki value and thinking about the plane formed by this direction and a normal to the surface. So I've now found that the incident, reflected and transmitted components are all in a plane together. Now, the electric field, this is a transverse wave, so there is no electric field along in any of these ways along the directions of propagation. And that's true also for the magnetic field. The electric and the magnetic fields must both be perpendicular to the direction of propagation of the waves for any of the components. So I can consider two cases. So in this first case, I've actually mislabeled this here. So this should be E perpendicular and this should be E parallel. Okay. So on the left-hand side, what I'm saying is that the electric field, this is a case where the electric field at the point where the incident wave comes up to this boundary, the electric field is perpendicular to the plane of incidence. So that means that the electric field here is pointing upwards, okay? It's pointing upwards, and therefore the magnetic field is pointing perpendicular to that direction. Okay, so by working out which way EI is pointing, I can work out which way BI is pointing. And similarly, if EI is also pointing up here, so if here EI is pointing down and ER is pointing up, I can now say which way the magnetic field is pointing in this way. And of course, if EI is pointing down here, it's also pointing down here, okay, into the page. And again, I can figure out which way the transmitted component of the magnetic field must be pointing there. So this is when the electric field is perpendicular to the plane of incidence. And here the electric field is parallel to the plane of incidence. So the electric field is in this plane formed by these three components. So that's the plane of incidence. The electric field is now pointing perpendicular to this direction, and the magnetic field must be pointing, in this case, which way is it now? It's pointing upwards, I think. And then the electric field in the reflected component must also match up with the magnetic field component, and so on. Okay, so we can compose an arbitrary polarization from a certain amount of this one and a certain amount of this one, but because we imagine the boundary conditions applying at this boundary, we will have a different relationship between the strength of the electric fields EI, ER, and ET in this situation compared to this situation. Now we also know that at z equals 0, we can write that the components of the wave vector in the x direction must all be equal to each other. So those are our way to calculate the amount of EI, ER, and ET. So let's do that. So we know that KXI, KXR, and KXT are all equal to each other at the boundary, but we also know that the magnitude of KXI, the magnitude of K in the x direction, must be equal to whatever the wave number is in medium 1 times the sine of the angle of incidence. And it's this, coupled with the same relation for the reflected component, of course they will have the same size of wave vector, it is this that allows us to obtain the law of reflection, which is that theta I equals theta r. For the transmitted component, we know that K2 is different in medium 2 compared to medium 1, and it's related to the magnitude of k in the x direction by sine theta t. So relating this component to this component for the incident wave, I can now derive the law of refraction, which is Snell's law, where of course I also have to make the substitution that I can replace the wave vector magnitude with the refractive index. So by considering the waves in each of the three components, the incident, the reflected, and the transmitted, and by thinking about the boundary conditions for those electric fields, I can obtain the laws of reflection and refraction. Now, the other thing I want to do is to look at the amount, rather than the angles, I want to look at the amount of electric field which is contained in the incident, reflected, and transmitted components. I want to know how much transmission and reflection I have, and I expect that it will be different for the two components, the perpendicular component and the parallel component. So in the case of the perpendicular component, this is what is known commonly as S polarized light, where S is the abbreviation of the German word Senkrecht, which means perpendicular. Because the electric field is normal to the plane of incidence, there are no cos theta terms in our boundary conditions. Therefore, the electric field at the boundary must be continuous, so that the summation of the incident and reflected components must be equal to the transmitted component electric field. However, the magnetic field lies at an angle to the boundary, so its continuity equation must have a cos theta component for each of the components, remembering of course that the boundary condition is for H and not for B, so I have to include the mu values. So combining these together, I can obtain a relation between the incident, reflected, and transmitted electric field magnitudes in terms of theta I and theta t, remembering that the reflected angle is the same as the incident angle. Moreover, because I know that the permeabilities in a dielectric are typically 1 in a non-magnetic dielectric, I can also relate the magnetic field to the electric field in this way, and I can obtain, by combining these ideas, I can obtain a relation between the magnetic fields, that's what I've got here, and I can use Snell's law, and this relation between cos theta t and 1 minus sine squared theta t, this is cos squared plus sine squared equals 1. I can work out the relationship between the reflected component compared to the incident component of the electric field. Remember, this is the case for perpendicular, the perpendicular component of the electric field. I can work out what the reflection coefficient is in terms of the incident angle of the incident wave. So this is one of the so-called Frener equations. So the way in which it is being expressed here is to write down n as being the ratio between n2 and n1, and I've also given it only in terms of the incident angle. So this is one way to write the Frener equations. There are other ways to write them where we think about the transmitted angles and the true refractive indexes, and also we can give it in other forms. But this is obviously a useful form because it allows us to calculate the magnitude of the electric field. So obviously the reflection, the intensity goes as rho squared. I can write down the magnitude of the electric field in terms of the ratio of the refractive indices and the angle of incidence. Now obviously I can do the same thing for the transmitted component, but that's not shown here. And I can also do it for the other case, which is for p polarized light, which means parallel to the plane of incidence. And in a similar manner to what we did for the perpendicular component, for the S polarized component, I take that the two permeabilities, the two relative permeabilities are 1. But the difference here is now that B is perpendicular to the plane of incidence. So my boundary condition for B gives me this relationship between the three field components. And the continuity equation for E now has the cos theta terms, because remember I'm applying the continuity to the component of the electric field which points along the boundary. So again, by combining these together, And knowing that I can relate the electric fields in this way, because of the angles of incidence, I can obtain this equation. And applying again Snell's law and this sine squared plus cos squared relation, I can obtain another one of Fresnel's equations, but this time for the parallel component of the electric field. And note that it has a different form. I still have the cos theta term here, but the difference is for the perpendicular component there is no n squared term, but in the parallel component there is an n squared. That's how they differ from each other. So again, there are several Fresnel equations. This is the one for the reflection coefficient. So there are a number of them. Now, let's just take a pause for a moment. So we've usually assumed that mu1 equals mu2 equals 1. So we're talking here about a non-magnetic medium. So let's think about these reflection coefficients and transmission coefficients in terms of wave impedance. So let's try to link together these ideas. Remember that we previously wrote for a dipole which was oscillating that we could relate its power, the power emitted, to the current squared. So Z was some kind of radiation resistance, and we said that the radiation resistance could be related to some fundamental constants combined together, Z0 equals mu naught C. We call this the free space impedance, which would allow us to calculate which allows us to calculate the radiation impedance for a particular antenna of length L when radiating a wavelength lambda. But we also know in free space we can relate the magnetic field to the electric field. Magnetic field equals the electric field divided by C for an electromagnetic wave moving in vacuum. Let's rewrite that in terms of H. So B equals mu naught H in a vacuum, which is equal to E over C. So therefore, the value of H is equal to E over mu naught C. So for a free space electromagnetic wave, the value of H is equal to E divided by the free space impedance. So why is that interesting here? Well, let's do another calculation. In a general dielectric medium, we can do a similar calculation, which is that the impedance of the electromagnetic wave is equal to E divided by H. But of course, in a dielectric, I can relate E to H in this way. I have to include the permeability and omega over K. And when I do that, I find that the impedance can be written as mu r mu naught divided by epsilon r epsilon naught, all square rooted. If I have a non-magnetic medium where the permeability is about 1, then I can write down this impedance, this relationship between the electric field and H, as being equal to the free space impedance divided by the square root of epsilon, which of course is just the refractive index. So an electromagnetic wave moving through a dielectric medium has a relationship between the electric and magnetic fields when expressed in this way, which is 1 over n, where n is the refractive index, another connection between the electrical properties and the optical properties. So we can rewrite Fresnel's equations in terms of impedances. So here are the Fresnel equations expressed in another way. So what we've done is we have expressed them in terms of now the incident electric to the incident angle of the incident wave and the reflected angle, the transmitted angle, and this is the reflection coefficient expressed in terms of theta I and theta t, and in terms of the two impedances which are related to the refractive indices. So for my two components, for my S-polarized component and my P-polarized component, I can express the reflection and the reflection coefficients for the S and P polarized components in terms of impedances, and I can now look at what this means if I have something other than a dielectric. So this is the general case, and I can now think about how this looks in terms of a conducting material. So in a conductor, I can write down the ratio of the magnetic to the electric field is K over omega. And we saw before that we can write down K over omega for a conductor in this way, for a good conductor. So we have mu naught sigma over 2 epsilon naught omega, and we have this complex term. So now we can write down what the impedance is when we apply it into the Frener equations here. The impedance is E over H, and when we write this all out, we can identify that we have mu r here, we have mu naught c, which is the free space impedance, and then we have this term here, which depends upon the conductivity and the frequency. And again, as per usual, we take mu r to be equal to 1, so that for a conductor, I can write down that the impedance of a conductor is equal to the free space impedance times some scaling factor to do with the conductivity and the frequency we're operating at, and we see that it has a complex term. Now, you can see here that the free space impedance has a certain value, and if I include a conductivity, we can see that mod z, the magnitude of the impedance of the conductor, is much less than z0 because the conductivity is large, because epsilon naught omega over sigma is much less than 1. So if we substitute that back into our Frener equations up here, and we remember that z1, for example, we imagine an electromagnetic wave incident upon a metal from, say, air. Z1 is going to be more or less the same as Z0, about 377 ohms or so. The conductor has an impedance which is much lower, and that tells us that we get complete reflection both for the parallel component and for the perpendicular component and for the parallel component of the electromagnetic field. So we see that metals are completely reflecting. In the special case of normal incidence, we can say in general that the perpendicular and parallel components have reflection coefficients which are given by, for the perpendicular, it's Z2 minus Z1 over Z2 plus Z1, and for the parallel component, it's Z1 minus Z2. So they are different, divided by Z2 plus Z1. So this is the general case of Frener's equations for normal incidence. And as you can see, that if Z2 is equal to Z1, in either case, there is no reflection. So this is analogous to what we have in a cable. If I have two cables which I connect them and they have different impedances, then if the impedances are matched together, then there is no reflection at the boundary between the cables. So we can see that the transmission and reflection properties of electromagnetic waves are analogous when we consider them in terms of the optical properties or in terms of their electrical properties when expressed in terms of these impedances.